Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone. So that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about In this video, I am going to discuss about a very important practical aspect of ferromanganese production in submerged arc furnaces, and the title of this video is The Behavior of Coke in Smelting Ferromanganese in Submerged Arc Furnaces. My dear friends, you might have heard about the coke importance of coke in the ferromanganese production. So in this video I will be describing in detail the characteristics and their behavior of coke in the production of smelting of ferromanganese in submerged arc furnaces. So this video will be completely detailed about the behavior of coke, so that it will be very easier for you to understand the importance of coke in the smelting of ferromanganese in submerged arc furnaces. So before I start this video, I would like to all of you to watch an important video which is presented in the next slide. So first please watch this video and then we will continue. observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. I hope my message in the previous slide is clear to you all, and I expect you all to keep always that in mind. And for this video I am starting with introduction, and here in this introduction I will be telling about some basic fundamentals of ferromanganese smelting in submerged arc furnaces. If you want a detailed presentation on high carbon ferromanganese production in submerged arc furnaces, the link is provided in the I button. You can check, and also that video is available in my channel. You can browse through my channel and find that video and get the detailed information about production of high carbon ferromanganese in submerged arc furnaces. So let's begin this presentation with introduction. The reactions and changes in the burden materials during the submerged arc furnace production of high carbon ferromanganese have been extensively investigated through both plant and laboratory scale studies. The excavation of a frozen furnace at the Meerton ferromanganese plant in South Africa in 1977 has provided considerable understanding of the changes in the burden materials and the nature of reaction zones. Details of the excavation procedure are given by Bagza et al. And studies by Corsaris on the excavation products revealed that the interior of the furnace could be divided into 9 zones, of which 3 appear to be of most importance in production and metallurgical processing. These are: first, a cone of fast descending burden around each electrode. Next, a coke bed directly below the electrodes. And third, last but not the least, a mixed coke slag layer beneath coke bed. In some early laboratory studies of carbonaceous reduction of iron ores, a technique to simulate the processes that occur in the shaft of the iron blast furnace was developed, which became known as the stationary charge in controlled environment, that is SICE for the acronym technique. Urquhart used the SICE technique to study the production of high carbon ferrochromium in a submerged arc furnace, and the technique was subsequently used by Grimsley, Dewar and C. and Corsaris and C. to investigate the reduction of South African Mammoth-1 manganese ore at relatively low temperatures using Delmas and Scott cokes. Examination of samples from the dig out of the Meerton furnace by Corsaris and Finn revealed that the mineralogical and morphological changes in the ore were similar to those that occurred in the SICE investigations. The major findings of that study were that between 1300 and 1600 degrees Celsius, reduction occurred in 3 main stages. First, rapid reduction of higher manganese oxides to MnO and the hematite to metallic iron in the solid state by carbon monoxide, and formation of a primary slag consisting mainly of CaO and SiO2. Next, dissolution of amino into the slag and reduction at the surface of ore lumps to form metallic beads, and third, reduction by lump carbon in contact with molten slag. In all previous studies of reduction of manganese ores to form ferromanganese, most attention has been paid to the behavior of the ore and little attention has been paid to that of the coke. Pistorius reviewed the role of carbon in ferroalloy production and highlighted the importance of the kinetics of carbon dissolution in the metal. The objective of the presentation is to investigate and demonstrate the behavior of coke in ferromanganese production in order to identify the desirable properties of coke for optimum furnace performance. The investigation was undertaken to attempt to explain the different furnace performance observed by metallurgists at the TEMCO plant, then operated by BHP Limited, now it is known as BHP Billiton Limited in Tasmania, Australia. For ferromanganese production, TEMCO operates two Elchem-made closed-top furnaces, rotating arc furnaces rated at 27 MVA and 29 MVA, and an Elchem 36 MVA stationary closed furnaces. The ferromanganese is produced from metallurgical grade lump manganese ore from Groote Eylandt in Australia's Northern Territory. Sinter produced from manganese ore fines on a Lurgi down-drop sintering machine at TEMCO, and iron ore for grade control. In the late 1980s, TEMCO metallurgists ran a series of campaigns using cokes from different sources and observed a range of furnace performance. For some cokes, the furnace was stable and productivity was high, while for others, productivity was low and the furnace behaved poorly. For example, the temperature of the top of the furnace increased by more than 300 degrees Celsius. The furnace off gas was high in hydrogen and sometimes contained volatilized manganese. The slag and alloy composition varied over a wide range. Graphitized coke was tapped from the furnace with the slag, and coke, electrode and power consumption rates were high. A selection of coke samples which exhibited a range of behaviors from good to bad furnace performance was supplied by TEMCO for the purpose of attempting to identify the characteristics of the cokes which caused the variation in performance. The investigation involved characterizing the cokes to determine their range of properties and performing a series of experiments in the laboratory to simulate the reduction of burden materials. Now let us discuss something about coke characterization, how it was done and what is its importance. The composition of the coke samples is given in the table 1 in the next slides, coming one. The Newcastle, Port Kembala and Whyalla cokes are blast furnaces cokes prepared at the respective steelworks in Australia. The Newcastle plant has subsequently been closed. The source of Japanese coke is not known. Use of Japanese and Newcastle cokes was found by TEMCO metallurgists to result in better furnace performance than use of the Port Kembala and Whyalla cokes. A microscopic examination revealed that the Japanese coke contained large quantities of isotropic and anisotropic fusible materials. So this is the table 1 which shows the composition of coke samples in weight percentage. You can pause the video and observe the table contents. Okay. The anisotropic material had the widest variety of mosaic textures ranging from fine to medium and coarse grain. It was concluded that the Japanese coke was made from a blend of low, medium and high rank coals and coke breeze. Newcastle coke contained a smaller amount of fusible material than the Japanese coke. The fusible materials also contained a narrower variety of mosaic textures. There was little isotropic material and no flow or patch mosaic texture. My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on. This indicates that the Newcastle coke was made from a blend of low and medium rank coals with no added coke breeze. The Port Kembala and Viola cokes were microtexturally similar and both contained larger quantities of non-fusible materials than the Newcastle and Japanese cokes. The blend from which they were produced contained a larger quantity of medium to high rank coal as revealed by the coarser mosaic textures. The non-fusible components in the Port Kembala, Viola and Newcastle cokes exhibited both isotropic and anisotropic properties. Fewer non-fusible grains were present in the Japanese coke than the Port Kembala and Viola coke, while Newcastle coke contained fewer non-fusible grains than Japanese coke itself. Rounded, oval and elongated pores were present in all the cokes. The rounded and oval pores were formed by degasification during coking, while the elongated pores were formed by interconnection of degasification pores also during coking or originated from the original coal. The Japanese coke contained the largest degasification pores and their walls were relatively thin. Pore size in the Viola coke was larger than in Port Kembala coke but smaller than in the Newcastle and Japanese coke. The pores in the Japanese coke occurred predominantly in the fusible components while they were present in both the fusible and non-fusible grains in the other three cokes. Now moving ahead, let us discuss about the strength of the cokes and their importance. A Tenius Olsen hardness testing machine was used to determine the strength of coke particles. The apparatus had two plates which were free to rotate in all directions so that the force exerted on particles was through their flattest surface. The tests were carried out on coke samples between 6 and 200 mm in diameter. Particles were tested individually and for each coke size fraction 10 measurements were made and then averaged. The values are shown in table 2 in the next slide. The magnitude of the standard deviation indicates there was a large variation in strength which is to be expected for non-homogeneous materials of irregular shape. The averaged results show that for each coke type, strength increased considerably with increasing size of particles. In the size range used by 10 coke, that is 6 to 19 mm, Viola coke was the strongest, followed by Newcastle coke with the Japanese and Port Kembala cokes having about the same strength. So this is the table which shows that average force and standard deviation required to break coke particles under compression. You can pause this video and observe the table contents. Okay, now let's move ahead. Okay, moving ahead, let us now discuss about porosity. In this coming slides, we will be knowing about the porosity and its importance and how it is measured. So porosity in coke is of two forms. First one is open, that is pores that are interconnected and which lead to the surface of the grain, and the second type is closed porosity. Open porosity was measured using a mercury porosimeter. Preliminary measurements indicated that the bulk of open porosity was in the size range of 10 to 100 micrometer. Closed porosity was measured using an IBAS 2000 optical image analyzer to examine polished section of coke. The pores were discriminated from coke on the basis of reflectivity, and closed pores were defined as all pores with radius less than 10 micrometer. 100 images were examined for each sample, which were processed separately and then averaged. The results are shown in table 3 in the coming slides. The total porosity of all the cokes was around 40%, with open porosity being the larger component in all cases. There was not much variation between the four coke types of the open and closed porosity, though the Japanese and Newcastle cokes had slightly lower open porosity and slightly higher closed porosity than the Port Kembala and Viola cokes. So this is the table which indicates about the open and closed porosity of the cokes as received in volume percentage. You can pause the video and observe the table contents. Okay, moving ahead. Now let us talk about something about reactivity. The reactivity of the cokes with respect to carbon dioxide, the Baudard reactivity, that is the equation CO2G plus C solid is equal to 2CO, first equation. This is called the Baudard reactivity equation, was determined at 1000 degrees Celsius on two size ranges of particles. The results are presented in the table 4 in coming slides. Reactivity is defined as the volume of CO2 at standard temperature and pressure that reacts with 1 gram of coke per second. I repeat, reactivity is defined as the volume of CO2 at standard temperature and pressure that reacts with 1 gram of coke per second. In practice, the reaction was carried out over a period of time and the reactivity averaged over the first 30 minutes and over the first 45 minutes as are given in the table in the coming slides. The weight loss of the coke samples after 55 minutes of reaction with CO2 is also given. So this is the table which indicates and demonstrates about the coke reactivity index at 1000 degrees Celsius for the as received cokes. As usual, you can pause the video and observe the table contents so for you get the better understanding. Okay, next, moving ahead. The results show that there are no significant differences between the reactivities of the cokes determined after 30 and 45 minutes, nor are there any significant differences between the reactivities determined on the two size fractions, except for the Viola coke. It is slightly more reactive in the smaller size ranges. Japanese coke is clearly the most reactive, followed by Newcastle coke. The Port Kembala coke is more reactive than the Viola coke in the smaller particle size range, but is about equal in reactivity in the smaller size ranges. The trends in weight loss after 55 minutes reaction are similar to the trends in reactivity. So now I am going to explain the experimental investigation of reduction of sinter burden. I hope I am going so far so good, and whatever matter I have discussed, it is clear to you all. The coke characterization results suggest that the strength and initial porosity of the cokes are not related directly to the performance of the cokes in the furnace. However, the reactivity of the cokes correlates well with the behavior of the cokes in the furnace, the more reactive cokes being reported to perform better than the less reactive cokes. An experimental program was designed to assess whether coke reactivity could affect the reduction behavior of the manganese burden. The program involved laboratory scale size tests to examine the reduction of furnace burden up to 1300 degrees Celsius and a series of reduction from lead experiments to investigate reduction in the higher temperature mixed slag coke zone of the furnace. So now let us discuss about the details of size experiments. The objectives of the size test is to provide conditions that simulate a batch of raw material descending through the upper part of the furnace shaft. For the test, a batch of approximately 500 grams of charge made up of the raw materials used by TEMCO and in the same proportion was heated in an aluminosilicate crucible in an induction furnace at the rate of 350 degrees Celsius per hour to a predetermined temperature, that is up to 1300 degrees Celsius, held at that temperature for 1 hour, then cooled under nitrogen. To obtain a reasonably homogeneous charge, the particle sizes of the raw materials used in the experimental program were approximately 1/10 that used in practice at TEMCO. The composition of the raw materials used in the test is given in table 5 in the coming slides, and the charge mixture used for standard conditions is shown in table 6. The experimental setup is illustrated in figure 1 in the coming slides. Considerable effort was devoted to developing a procedure that gave reproducible temperature profiles. The crucible which charged the thermocouple was weighed before each test and again after cooling at the completion of each test. I repeat, the crucible with charge and thermocouple was weighed before each test and again after cooling at the completion of each test. So this is the table 5 which indicates composition of raw materials used in the size test, that is mass percent. You can pause the video and observe the table contents. And this is the table which describes about mass and sizes of raw materials used in size experiment. And this is the schematic diagram of the crucible assembly used for the size experiment. Okay, moving ahead. At the completion of the test, the contents of the crucible were emptied into a metal tray and sieved to separate out the unreacted coke, which could be easily separated due to its smaller size fraction. Limestone, identified by its white color, was then separated by hand, and the unreacted iron ore was separated using a magnet. Sinter and manganese lump ore were not easily distinguishable, and generally both were greenish in color after reaction. However, the porous structure of the sinter helped to distinguish it from manganese ore. Each component recovered was weighed and representative samples of each were taken for analysis and characterization. So now let us discuss about mass loss results. The mass loss results for the crucible and contents due to reactions releasing volatiles, predominantly CO2 and CO, are shown graphically in figure 2 in the coming slides. Coke mass loss is shown in figure 3 in the coming slides. As expected, the total mass loss and mass loss by the coke increased with the final temperature achieved, but interestingly, there is a significant difference in the mass loss achieved at each temperature, depending on the coke type used in the experiment. The trends for total mass loss and coke mass loss are consistent and strongly indicate that the rate of reduction of the burden materials in the experiments was controlled by the Baudard reaction since the order of the degree of reduction is similar to the order of the reactivity of the coke towards CO2 at 1000 degrees Celsius as shown in table 4. So this is the figure of total mass loss of crucible contents in the size experiments, and this figure represents the mass loss of coke component of the size experiment. Now let us discuss about the changes in limestone, iron ore and sinter. Examination of the products from the 900 degree Celsius series of tests revealed that all the limestone had decomposed to CaO and the iron ore, which was initially hematite and geothite, had partially transformed to magnetite and woostite. At 1100 degrees Celsius, some reduction of the iron ore to metallic iron had occurred in all cases. For Japanese coke, all the iron ore had been reduced to metal, and for Newcastle coke, iron oxide that remained unreduced had converted fully to woostite, whereas for the other cokes, some magnetite remained. At 1300 degrees Celsius, all of the iron ore had been reduced to globules of metal for all four cokes. The metal globules typically contained about 16 weight% manganese and 4 weight% carbon. The unreacted sinter consisted of hospenite Mn3O4, Jacobsite MnFeO4, tephroid Mn2SiO4 and some MnO. At 900 degrees Celsius, the hospenite and Jacobsite in the sinter from Japanese and Newcastle coke tests had converted to MnO, while those reacted with the other cokes had only partially converted. At 1100 degrees Celsius, all remaining hospenite and Jacobsite had converted, and some metallic prills of iron containing 10 to 38% manganese had formed. These were typically 35 to 50 micrometer in diameter, and the relative amount of metal was highest for the Japanese and Newcastle cokes. At 1300 degrees Celsius, partial fusion of the sinter had occurred. The amount of metal had increased further, though the relative amounts were higher for Japanese and Newcastle cokes, and the metallic prills had increased in size to typically 50 to 100 micrometer and contained 30 to 40 weight% manganese. Now let us discuss about changes in coke properties. At 900 degrees Celsius, Japanese coke had the greatest and Port Kembala coke the least changes in microstructure and texture. Both the fusible and non-fusible materials of the Japanese coke showed signs of reaction, whereas in the other cokes only the fusible materials showed signs of reaction. At 1100 degrees Celsius, the microstructural changes were greater than at 900 degrees Celsius, and the pore sizes were usually much larger. Serration occurred in the fusible and non-fusible materials of the Japanese coke, while in the other cokes only the lower rank non-fusible material became more reactive. At 1300 degrees Celsius, most of the Japanese coke had eroded to small fragments due to serrations on the core peripheries. The non-fusible materials in the other cokes were the initial points of reaction leading to erosion or fragmentation. The change in open porosity of the reacted cokes is shown in figure 4 in the coming slide. So this figure shows the open porosity of reacted cokes determined by mercury porosimetry. I hope this picture is clear to you all. I have just explained the details of it. Okay, let's move on. The reactivity towards CO2 at 1000 degrees Celsius of the 4 cokes reacted at 1100 degrees Celsius and 1300 degrees Celsius was determined, and the results are presented in table 7 in the coming slide as mass loss after 55 minutes reaction with CO2. The results show that the cokes from the 1100 degrees Celsius size series had reactivities about 2 to 3 times higher than the S received cokes, and that the reactivities increased further in the 1300 degrees Celsius series but tended to converge in value. This is consistent with the results in figure 3, which shows that there was greater spread in the mass loss values of the 4 varieties of coke at 1100 degrees Celsius compared to 1300 degrees Celsius, that is 9 to 20 gram compared with 23 to 27 gram respectively. This would be expected if the Baudard reaction was rate limiting in the temperature range 900 to 1300 degrees Celsius. So this is the table which shows that reactivity as percent weight loss of coke after 55 minutes reaction with CO2 at 1000 degrees Celsius and of coke samples from the size experiments. I have just explained the details of it, so you can pause the video and observe the table contents. So now let us discuss about the reduction from melt experiments. To simulate conditions for reduction of MnO-rich slag in the lower part of the furnace, higher temperatures than could be achieved in the size experiments were needed. An upper limit of about 1300 degrees Celsius was imposed on the size experiment because above that temperature the crucibles were excessively attacked by the slag, contaminating the slag, and at higher temperatures failing to contain the slag. An approach was used in which enriched slags of the composition likely to occur in the first formed slag were reacted in hollows created by drilling into lumps of coke. In this way, the coke acted as the container for the slag as well as being the reductant. As received coke was used for these tests because of the coke recovered after the size experiments was too porous and weak. Finely ground ferromanganese slag from Tenco was doped with MnO2 and Fe2O3 powders mixed with a stoichiometric amount of powdered carbon to form MnO and FeO and remelted under nitrogen. The resulting slag of composition is shown in table 8 was reground and used in the reduction from melt experiments. In an experiment, about 10 gram of the enriched slag was poured into the hole in a lump of coke which was placed on a bed of alumina powder in a silicon carbide tray, then covered with an inverted aluminosilicate crucible. The assembly was placed in an electrically heated muffle furnace programmed to heat at 1500 degrees Celsius per hour and heated to 1500 and 1550 degrees Celsius. It was held at that temperature for 15 minutes for the 1500 degree Celsius tests or 30 minutes for the 1550 degree Celsius tests. Then the furnace was switched off. The cooling rate of the furnace at high temperatures was about 80 degrees Celsius per minute, which ensured that the crucible contents solidified in less than 5 minutes after switching off the furnace. The reacted crucibles were one section being used for microscopic examination, the other for chemical analysis. A typical section of a crucible is shown in figure 5. An equilibrium experiment was also performed using a Port-Kembara coke crucible which was heated to 1500 degrees Celsius and held for 12 hours. So this is the table which shows the composition of the enriched slag used for reduction from melt tests in weight percentage. So this is the table with all the figures, and this is the photograph of the products of a typical melt reduction tests. So you can pause the video and observe this very carefully. The degree of reduction can be followed by the Mn to Fe mass ratio as shown in table 9. FeO is more easily reduced than MnO, and hence the higher the Mn by Fe ratio, the greater the degree of reduction achieved. The results show that for the 1500 degree Celsius series, the degree of reduction follows the initial order of reactivity of the cokes with a range of Mn by Fe ratios from 1/8 for Port-Kembara coke to 5.4 for Japanese coke. The Mn by Fe ratio for Japanese coke is similar to that for the equilibrium test. However, for the 1550 degree Celsius series, the effect of the initial reactivity of coke is small, the range of final Mn by Fe ratios being only 3.8 for Port-Kembara to 5.1 for Japanese coke and closer to the equilibrium value. So this is the table which depicts the details which I have just explained. Composition of alloys produced in the reduction from melt experiments in weight percentage. You can pause the video and observe the table contents. The results indicate that attainment of the equilibrium of the reaction MnO plus Fe is equal to Mn plus FeO is rapid once molten phases are formed with Japanese coke attaining the equilibrium Mn by Fe ratios at 1500 degrees Celsius within a little over an hour of total reaction, and other cokes approaching the equilibrium ratios in the 1550 degrees Celsius tests. Silicon reduction was far from the equilibrium value, and this is consistent with the knowledge that silicon equilibrium in iron making is slow to attain. Note that the carbon content of the alloy from the equilibrium test is lower than for the other tests because silicon suppresses the solubility of carbon. So now, based on all these investigations, and let us have some discussion. Carbothermic reduction of MnO and FeO are endothermic reactions, but MnO reduction requires more heat than FeO reduction. As given in the equation, MnO solid plus C solid is equal to Mn liquid plus CO gas delta H is equal to delta H degree is equal to 276 kilojoules at 1200 degrees Celsius. And again given the next equation is FeO liquid plus C solid is equal to Fe solid plus CO gas delta H is equal to 149 kilojoule at 1200 degrees Celsius. MnO reduction also requires a higher minimum temperature where delta G degree is equal to 0, 1400 degrees Celsius for MnO and 720 degrees Celsius for FeO. In practice, the thermodynamic activities of manganese and iron are less than VDT due to alloy formation, so the actual minimum temperatures will be slightly lower. In ferromanganese production, therefore, it is thermodynamically possible for the iron ore to be reduced to iron, the higher manganese oxides to be reduced to MnO, and some of the MnO to be reduced to manganese dissolved in the metallic iron at low thermodynamic activity in the solid state under the conditions in the shaft using the sensible heat and reducing capacity of the gases produced in the slag coke zone. This would leave only the reduction of the remaining MnO to occur in the high temperature mixed slag coke zone. The results of the size and reduction from melt experiments reveal that the rate of reduction of iron oxide to metal and the reduction of the higher oxides of manganese to MnO are strongly controlled by the Baudard reaction under conditions that exist in the shaft of the submerged arc furnace at temperatures up to about 1300 degrees Celsius. The rate of reduction of MnO to alloy is much less controlled by the Baudard reaction, since at temperatures where most of the MnO is reduced, that is above 1300 degrees Celsius, the reactivities of the coke, irrespective of the initial values, tend to converge to broadly similar values as shown in table 7. The height of the shaft of a submerged arc furnace is much less than that of an iron blast furnace, and the residence time of the burden in the shaft is proportionately less. Typically, reduction of oxides to metal must be performed in a few hours compared with 6 to 8 hours in an iron blast furnace. Use of a reactive coke in submerged arc furnace production of ferromanganese allows the iron oxide to be reduced to metal, the higher oxides of manganese to be reduced to MnO, and a small amount of the MnO to be reduced to manganese dissolved in iron by the time the burden reaches the mixed slag coke layer below the electrodes. The lower height of the shaft relative to that of an iron blast furnace also means that the strength of coke is a less critical property in submerged arc furnace smelting of ferromanganese than in iron blast furnace smelting. It is now possible to postulate a model to explain the observed poor performance at TEMCO when the lower reactive cokes were used. When a low reactive coke is used, less reduction of iron oxide and of the higher oxides of manganese will occur in the shaft, and a higher proportion of coke will survive and accumulate around the electrodes, resulting in a deeper coke bed. This will decrease the burden resistivity and lead to higher temperatures and greater heat generation in the hearth. This in turn will lead to volatilization of manganese metal and increased off-gas temperature and greater reduction of silica. At the same time, power and electrode consumption will increase and coke particles will gravitize and become less reactive. Due to the less reactive nature of the coke and the relatively short residence time of charged materials in the earth, incomplete reduction of MnO will occur, leading with the increased silica reduction to poor alloy and slag chemistry control and to unreacted coke being tapped. So now let us come to conclusions. Previous studies on the behavior of burden in the submerged arc furnace production of high carbon ferromanganese have focused on the metal forming constituents. Little attention has been given to the properties of the coke required for good furnace performance. The overall conclusion of this study is that the coke selected for use for ferromanganese production in submerged arc furnaces should be more reactive as measured by the conventional Baudard reactivity test at 1000 degrees Celsius than those normally used in the iron blast furnace. Use of these cokes should result in stable furnace operation and good productivity. The reason for this is that more reactive cokes will enable Baudard controlled reactions to be completed higher in the shaft, thereby more effectively utilizing the sensible heat and reducing capacity of the gases from lower in the furnace and enabling the final high heat demand reduction of MnO to Mn to be the major reaction in the high temperature mixed slag coke zone. Conversely, less reactive cokes may lead to poor reducing conditions and larger coke beds in the furnace, resulting in poor furnace control, unstable alloy and slag compositions, and higher power consumption. Based on an examination of the cokes studied, it is further concluded that cokes with the desirable attributes could be produced under appropriate coking conditions from a blend of low, medium and high rank coals. This will produce cokes of intermediate strength, high porosity and high reactivity relative to iron blast furnace cokes. Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else, for gaining popularity in my channel. So you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.